so before we start, so why are we having these lectures? Because there are a lot of different topics of algorithms in data structure which are not covered in any courses. So I just can't find any video lectures about these topics. They're covered in some papers, but nobody read papers. Yes, it's 2021. No one is reading any scientific papers now. Everybody is watching YouTube videos. So I just want to to fix this and just transfer some classical algorithms works to the YouTube. So anyone who is interested in algorithm data structures can find these lectures on YouTube and just learn something interesting. Okay, so today we discuss a classical work of Robert Arjan about a union-find data structure. I posted the link to the paper in the blog, in the Code Forces blog. So you can open the same paper just to find out those. So it is little bit, no, it is very cool paper. So I highly recommend it for everybody to read it. But it's at some points it's a little bit overcomplicated. So I will try to simplify it a little bit. I just get rid of any corner cases and any not very important constants and so on. So just to make the proof more simple. But if you want to read the real article, I highly recommend this this paper. Paper is great. Cool. So what are we talking today? Today we talk about union-find data structure. All in competitive programming sometimes it's called the disjoint set union. So what is the data structure? You have two operations. You have operations union x, y, and find. And the current state of your data structure is some sets. So you have some sets. So find operation returns the set which contains element x. So you have element x. And find operation gives you the set which contains element x. And union operation just make union of two sets. So you have two elements x and y. And when you call the union operation, these two sets will combine into one. So you merge these two sets into one big set like this. So these are two operations, union and find. How do you implement the union-find data structure? Again, like we discussed in the previous lecture, it's quite easy. So we will implement the union-find data structure in the following way. We will maintain each set as a tree, and like this. So here we have two sets. We have one set of 1, 2, 3, 4, one set of 5 elements and another set of 3 elements. And the root of the tree is the representative of this set. So usually you have linked to here something like that. So this element is representative of the set. Now, how you implement operations union and find? For operation find, you simply go to the root of the tree. And this tree represents the set which contains element x. So for operation find, you simply take the element x and follow the path to the root of the tree. And this element will represent the set which contains element x. How to make union operation? First you find the roots of corresponding trees. So you first find them minus union. So you have element x, element y, you follow the path to the root, you take the root of one tree, the root of another tree, and then you just make link from one root to another root. So you can make it like this. Yeah. And now these two trees combine into one big tree, right? So you have like one tree, another tree, You have x here, you have y here. You follow the path to this root, then you make this link. Now you have one big tree, right? Like this. That's basically all you need to know about union find data structure. It's very simple to code. The algorithm is actually one of the simplest algorithms we learned during the first semester. That's all. That's how it works. And now we apply to make it work fast. We apply two heuristics. Yeah. First heuristic we used was the rank heuristics. Heuristic. English is difficult. So rank heuristic works like this. We try to make these trees balanced. So when we make union of two sets, we need to make this link from one tree to another tree. We will always make the link from the smallest tree to the biggest tree. So we will maintain, so let's see, we have one tree is small, another tree is big. We will calculate this height. This height we'll call the rank of the tree. And now we'll look on these two roots, check which root has smallest rank, and if rank of x, this is x, this is y, if rank of x is less or equal than the rank of y, then we will make link from x to y. So we'll always make link from small tree to big tree, right? This heuristic help us to maintain all the tree balanced. So if we always have small tree to big tree, the tree will always be kind of balanced. Okay? So the rank will be up to logarithm and so on. Okay? Cool. And the second heuristic we used was path compression. Path compression works like this. When we call find operation, so we start from x and follow the path to the root of the tree. We at the same time change all the links to the root, from the parent to the root. So we just, for each edge from the node to its parent, we remove this edge and add edge to the parent, and do it for all, and here's also. So we remove all these edges and make the edges to the root of it. That's called the path compression heuristic. Pretty simple, right? Okay, everybody on the same page, right? Everybody know what's going on. Cool. Any questions by now? Rank is the height of the tree, right? Yes. The rank of the node is the height of corresponding tree. So if you have vertex x, have some tree, so this height of the tree is the rank of x. And you can maintain these ranks when you make the union operation. So when you how to change ranks? When you this rank is do not change when we make path compression. So these ranks are we don't maintain the real height of the tree. Yeah. So when you make path compression, you may change the real height of the tree. So you have like here. You have here you have vertex of rank 2. If you call find from here, you will apply path compression and you will change this link to here. When we do something like this, we will not change the ranks because it's complicated. So we will leave the ranks as they were before we apply all the path compressions. So these ranks are not affected by these path compressions. That's yes, you can do this. You can do the same heuristics based on the size of the tree. Yes, you can calculate the size of both trees and link tree of smallest size to tree of bigger size. That will also give you the same asymptotics. I just need the ranks for my analysis, so I will keep the ranks. It's easier to make the analysis of this algorithm when I have these ranks. So I will have the ranks heuristics. You can do absolutely the same when you calculate the size of tree. You can calculate the size of these trees and connect small tree to big tree. It will give you the same time complexity, right? My code didn't work aside, but work is wrong. That's strange. It should work with both. No. Well, if you look at the heuristics, they do basically the same. They try to keep the tree balanced. If you link a tree of small size to a tree of big size, you have the same balancedness of the tree. Let's say like this. So no, you can use size heuristics as well. It will work exactly the same. Maybe you have some bug, I don't know. It should work. Cool. Now, what is the plan for today's lecture? Today we will prove the time complexity of the following. First, we will prove that if you use only path compression, then the time complexity is good. That's the fancy. What is good, we will talk about a little bit later. And the second thing we will learn is that if you apply both these heuristics, if you apply rank heuristics plus path compression, then time is even better. I'll give you the exact formulas in the end. Just they are not that simple. So usually during the standard course we prove the following time complexity bounds. We prove that if you apply path compression, the time complexity is log n. So usually what we do during the normal course, we'll prove that here it is log n, and here it is big O of iterated logarithm of n. So usually I prove on only this time complexity bounds because it is very simple to prove them. Today we'll prove slightly more accurate time complexities. Okay. Cool. Did I forget anything? It looks fine. Whew. Okay, that's the plan. That's the plan. Ready? Let's go. How? First, let's make some preparations. To make the analysis easier, I will do the following. So let's just. First, I will calculate only the total time. So what happens? You have n elements, and you have n elements. and you apply m operations, but the number of union operations is always n minus 1, yeah? You have n minus 1 unions. So the number of union operations is always the same. There are some n elements. Every time you combine two elements, the number of sets is decreased by 1, so you cannot have more than n minus 1 union operations. But the number of find operations may be different, and we will add another variable. Let's see, have m find operations. Finds. And our time complexity formula will depend on two variables. So we have first variable is the number of elements, and another variable is the number of finds. Here in this time complexity, we have only n here. N here and n here. That's kind of boring, yeah? Because the true power of this data structure is that the time complexity is decreasing when you make more operations. Like, more operations you make, the less time complexity is of these operations. So if you apply, like, if you have small number of elements and you apply many operations, many find operations, then because each time after the find operation you kind of make this tree better and better, then the time complexity is decreasing when you increase the number of operations. So I will make the time complexity, I will prove time complexity, which is some function of n and m, which is decreasing when m is increasing. So when m grows, the time complexity will be decreasing. No, I will explain what is an Ackermann function. Yeah, in a little bit. We will do everything. No, I will explain everything. That's the point of this lecture. Let's go. So, first, I will calculate only total time of all finds. So I will calculate only total time of all finds. So, this is the only thing I will calculate. Yeah. Why it is the only thing? Because unions are simple. You have only n minus 1 unions, and time complexity of union is constant. You need to make two finds, and then you make one. So unions are simple. If you optimize the finds, you will have the first union. And I will calculate only the total time, not the time of every single operation, because I try to calculate the amortized time. And these time complexities are amortized time complexities. So when I need to calculate amortized time complexity, I will calculate the total time, then divided by m. So if you get the total time, then divided by m, we will have amortized time. Yes, you can include all these unions in finds. Yeah, you may think of m as the sum of all unions and all finds, like total number of operations. Yes, and for simplicity, I will think that m is at least n, because if you have less than n operations, it's kind of strange. There are some elements which you didn't access at any time. You may just remove these elements. And it is at most n squared. Because if you have more than n squared operations, then after each union you get more than n finds. It's kind of strange. If you call find from the same node twice, the second call will work in constant time, because you already make this link from here to here. So if you between two unions make two find of the same x, so you have this union, then you have find of x, then another find of x, and then another union. So this second find will obviously work in constant time, because during this find you make this thing from here to here, so this find works in constant time. So if m is more than n squared, it's also not interesting. So I will assume this just for simplicity of the proof, because at some point I will try to take logarithm of m base n, and I want this logarithm to be positive, yeah, because it's kind of strange to have negative time complexity. That's all. So that's only to make this proof a little bit simpler, just to avoid all the corner cases and so on. It's not that important. This data structure works even if m is less than m, or if it is greater than n squared. It still works. Now, the easiest way to calculate this total time of all find operations is to think about it as the following. Let's first make all the union operations. Yeah. So let's start with single nodes and then perform all the union operations one by one. So in the end, we'll have some big tree of all elements. So let's first make all the unions we need to make, just for analysis. It's again, the algorithm is simple. Now I'm talking about the analysis. You don't do this in your code. It's only for analysis. Yeah. So let's think about our data structure like this. If we first make all the unions we need to make, let's look on this tree. Let's apply all the ranks. So we build this tree and find the ranks. Oh, so rank 0, rank 1, 0, 2, 0, 1, 0, 2, 3. So let's build this tree. Again, this tree is the tree which we have in the end of the data structure. So we start from single nodes, we make all the unions, in the end we have this tree. Now, what happens when we make find operations? At some point we will make some find operations. So we just take this vertex and call it find operation. What happens when we call find operation? We follow the path to the root, but not to the root of this final tree, but to the root of the tree which was when we have this find operation. So when we call this find operation, we don't have this final tree. Yeah? We have some part of this tree. So we start from this vertex x and follow the path to the vertex which was the root of the tree when we call this find operation. Right? No, you can think about it like this is like this is the sketch of the final tree, right? Yeah. So this is the sketch of the final tree. You perform some operations, you perform some finds and some unions. So at some point you make like union of these two vertices, then union of these two vertices, then this union, then let's say this union, we have to start from what? From this union. So these bold edges are the current state of your data structure, right? That may be a little bit overcomplicated lecture, but I hope you're fine. When we call this find operation, we have this state of the data structure. So these bold edges are the edges which are really in your data structure. And these dashed edges are the edges which we will add later. Good. So what happens when we call find operation from some node? We follow the path to the vertex which is now the root of this tree, and apply the path compression. So we follow this path and apply the path compression. So we change these links to here. That's what's going on. Right? So again, how do you call find operation? Find operation looks like this. We have vertex x. We have some real edges and some, we'll have some more. And here some dashed edge. Yeah? So when we call find from here, we follow the path until we reach first dashed edge, and then apply path compression. So we change all these edges to here. It's already here. No, just for simplicity. Cool. That's basically all we need. Now, to calculate the total time of all finds, we need to calculate the total lengths of all paths which we travel when we modify operation. So when we make find operation, we travel through this path. So this path, the length of its path is added to a time complexity. Let's see. It's delta time. So you need to add the length of this path to your total time complexity, right? That's what's going on. And this is what we're trying to calculate. We're trying to calculate the total time of all find operations. The time of find operations is the length of the path we travel when we start from vertex x and end in some vertex which was the current root of the tree which contains element x. So we start from vertex x, travel some edges to the root, and then apply path compression. And this length is added to the time complexity. That's all the preparations. Now we'll actually calculate time complexity. Go. Again, let's stick here a little bit more. So, how we'll calculate this time complexity? We need to calculate the total lengths of all paths. Yeah. So instead of doing this, we will calculate this sum as following. We take vertex x. This is parent of x. Yeah. And for each this edge, we will calculate the total number of paths which include this edge. Yeah. So for each edge, we will calculate the total number of times we travel through this edge. Actually, for each x. It's like this. We will calculate. We'll take each vertex x and calculate the total number of paths which go through this vertex x. So for this vertex, we calculate how many times we travel through vertex x when we perform some find operation. So we have this vertex x. At some point, we perform some find operation from here, yeah, and go somewhere here. When we follow this path, we walk through this edge. Right? So we will just, for this edge, we'll increase time complexity by 1. So here, time complexity will be increased by 1, right? So we will calculate for each vertex x the number of times we travel through this edge when we perform some find operation. Now that's exactly what we'll calculate right now. Got it? Okay. Hope it's clear enough. Now let's go. Now let's calculate time complexity. Now, to calculate time complexity, we'll do the following. Let's go. First, we'll pick two values. We'll pick value b and value z. Value b will be equal to m over n, and value z will be equal to logarithm n square over m divided by logarithm m over n. Okay, now things got a little bit awkward by now, but that's fine. Now I can just pick two values and then make all the calculations, then pick these two values in the end, but it's easier to think about this like they got from some magic. So let's pick these two magic values. Yeah. So these two values I picked to make the final time complexity good. I just know what the final time complexity will be, so I know how to pick these values. But you can make all the same calculations and then pick these two values to find the optimal time complexity in the end. But I know what this time complexity will be, so I will pick this value before. Okay. And now we will do the following. Let's write the following sequences. Let's find. Let's say. Let's do it like this. Let's do it like this. Yeah. Let's pick the following sequences. Let's have the sequences 0. It will be 0, 1, 2, 3, and so on. Pretty simple. Sequence 1 will be b. No, 0. So start from 0. 0, b, 2b, 3b, and so on. Sequence 2 will be 0, b square, 2b square, 3b square, and so on. And so on. So the sequence number j will be the following. We start from 0, then see b in power j, then 2b power j, 3b power j, and so on. Yeah, so we make z such sequences. Okay. It looks like magic for now, but it's fine. I will explain everything just in a minute. So the final sequence will be 0 b power z, 2b power z, 3b power z, and so on. Good. Now let's look on some edge. So let's have vertex x, and we have the edge to its parent, vertex y. So y is the parent of x. How did Tashan come to this? I have no idea. This all looks like a simple magic, right? That's cool because the code is very simple, but the proof is like magic. Now, let's look on this edge. Let's assign classes to all edges. So let's say for this edge, have some class equal to k. So let's say, so here, let's say edge x, y have class k. If the following is, if let's look on ranks of x and y. So these two nodes have some ranks. Let's say that this edge belongs to class k if these ranks both can be fit between two consecutive values of the kth sequence. So we take sequence. Let's take j. Let's save some letters for future. So if we have, let's look on this sequence number j. If we can fit ranks of these two vertices between two consecutive values of this sequence, we will say that the rank of this edge equals to j. So it is minimal j such that these two ranks may be fit between these two vertices. Let's say, so it's k multiplied by b in power j is less or equal than rank of x, less than rank of y, less or equal than k plus 1 b power j. What happens if these numbers are not integers? That's a good question. I think you need to round them up. I told you I will avoid all the details. If you want to read the details, I think you need to round these values down. Also, I don't want this b to be equal to 1 because it's kind of strange. So I maybe want to have. So in the real world, I think you need to have something like this. Maybe you need something like this to avoid all the corner cases when m is too small and this number is close to 1. So I think it's better to have something like this in the real. You can read the real paper. Let's check. Let's check what b's you have here. When do you introduce the b? I missed the part when the b is introduced. That's very lazy lecture, yeah. That's not the lecture which was prepared like a few years ago. So I will sometimes consult the paper. Oh, I missed this part. I think it should be something like that. I'm not sure. Again, these corner cases are not that important. So if m is small, it's obviously broken. So it's not that important. But if you want to have a good paper, you need to avoid all stationary cases. No, I just missed this. So when do you introduce b? I don't know. At some point, that should be variable b. Sorry, I can't find it. Fixed later. Okay, later. Okay, let's check later. Okay, they do it like I discussed in the first place. So they first make all the calculations for some integers b and z, and then in the end they pick the correct values of b and z. But where is it? So at some point you need to pick. Where is it? Oh, yeah, I was close enough. So they they pick it like this. Yeah, and here we make maximum of this and 1. It's rounded up. Why not? Like this. So you need to make some accurate tweaks when you want to your formulas work for small values as well. But I will just avoid all stuff like this, just for simplicity, because this is, I try to simplify this proof as much as possible. Okay, so in the real paper you need to do something like that to avoid all these corner cases. Okay, let's go back. Let's go back. Now, here, this is how we assign the classes to all edges. Yeah. So again, you take some edge, you find the ranks of these two nodes, and you find the smallest j such that these two ranks may be fit between two consecutive values of this sequence. The easiest way to think about it is like the following. Well, let's say, for example, let's say b equal 2, for example. Okay? So first you have numbers 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. That's for sequence number 0. Then next you will have sequence 1, 2, 4, 6, 8. Then you have sequence 1, 4, 8. Then you have sequence 1, 8, and so on. So it's something like that. And now you have some edge. This edge have two vertices. You find the ranks of these vertices and find the smallest number such that these two ranks can be fit between. So like you have. So this is rank of x. This is rank of y. So you need both these ranks to fit between these two consecutive values. And if you can fit it here, then this is class of x. Is it clear by now? Again, what's going on? We take some edge, calculate these two ranks. You may think about these ranks as the segment on the line. So if you have this line, let's have this. This will be, this is the excess of all possible ranks. Yeah? You have rank of x and rank of y. You find the smallest layer such that this segment is between these two partitions. Yeah? So you have partition here, partition here. They split all the numbers line into some segments. So we need both these ranks to be in the same segment. If we go far enough in a single sequence, let's say sequence equals 2, we won't be able to fit around between that sequence. I don't get it. If we go far enough in a single sequence, let's say sequence of class 2, won't be able to fit in between that sequence. Let's say we go till b, so the two big number will be able to. Don't get it. No, yeah. For some edges, we cannot assign classes like this. Yeah, if the spread between x and y is too big, it may be not possible to find the correct sequence J. This J should be from 0 to Z. Yeah. So we want to find one of these sequences. It is possible that the difference between these two ranks is too big, so we cannot fit both these ranks inside one of the sequences. It's possible. So if there is no such J, we will assign the class equal to Z plus 1. So if there is no such J, then class will be equal to Z plus 1. So we will add all these big edges into one separate class. Yeah, good. Is it clear enough by now? Again, so we take each vertex, look on this edge, and try to assign some class. How we assign the class to this edge? We look on these two ranks and try to find the first sequence such that we can put both these ranks between these two partitions. If we put them in partitions and we find the smallest such class, then we assign this class. If we cannot put these two ranks between two partitions in all these Z sequences, then we say that the class equal to Z plus 1. So we will put all, so there may be some really big, so this is rank of X, this is rank of Y. So if the segment is too big, we cannot put it anywhere, so we just assign class Z plus 1. Yeah. That's all. That's all. Cool. Now let's calculate the time complexity. So what happens when we make fine operation again? So here's X. We call the fine operation from this X. So we follow this path to some current root. Let's look on the classes of these edges. So all these edges have some classes. Let's say class 2, 3, 1, 3, 2, 4. Is it possible to have such a class? No idea. Maybe it's possible. Segment matrix. No. The difference of these ranks may be more than one. The rank of Y is always greater than the rank of X. So rank of Y is always greater than rank of X. That's true. But the difference is not always one. Rank is not changing. No. Ranks are always the same. Ranks of all vertices, we pick the ranks when we build the final tree. So we make all the union operations, then pick the ranks of all vertices. We will never change the ranks of the vertices. So every vertex have some fixed rank. Okay, so these ranks are fixed. We will never change the rank of the vertex. We assign the ranks when we build this final tree. So we build the final tree after all the union operations, and then assign the ranks. And we never change the ranks of the vertices. Okay. Now we assign these classes. let's look on the classes of the edges. So we start from here, go to the root, and look on these classes. First, let's take the last edge from each class. So, for example, we have here, let's look on all edges of class 1. So we have one edge from class 1. Let's take this. From class 2 we have here and here, so let's take this. From class 3 we have this and this. Take this. That's another 3 to make it more interesting. So these edges are the last edges from their class. Want to change? Watch it. Rank is never changing. Class may be changed. Class will change. Rank will never change. Yeah. Again, let's go back. So the rank of the vertex is fixed, right? The class of the edge will change it after we apply some fine operations, because we make some path compressions. So parent is changing. So for vertex X, the vertex Y is changing because we linked it to different parent. So this vertex, this parent of X will change. So the class of X will be changed. Yeah, but the ranks are always the same. I did not use any properties of the ranks by now. The only property of the ranks I use is this, that the rank of the parent is greater than the rank of the child. That's the only property I use by now. So let's go here. Again, I want to calculate for each edge the number of times I go through this edge during the fine operations. So let's look first on the last edge from each class. Let's calculate these edges first. How many edges on this path are the last edges from the corresponding class? Operation afterward, when we call find operation, will not change the object. Okay, that's we assign ranks based on the tree without any path compressions, right? So we make all the unions, then assign these ranks. Cool, yeah. So when we assign these ranks, we used this not compressed tree. And then we fixed all these ranks and we will not change them in this proof. Again, this all is just for the proof. Yeah, it's not how you're supposed to implement your algorithm. It's basically just to prove that algorithms works fast. You don't need these classes in your algorithm. You don't need this. You need these ranks if you want to have rank heuristics. But this proof is not used rank heuristics. This proof is only for path compression actually. So you don't need ranks in your algorithm. You don't need classes. This only for the proof of time complexity. What about find functions in this union? Okay. Hope it's clear now. I don't know how to explain it more carefully. So again, what happens? You build this final tree after all the union operations. If you make union operations without any path compression, yeah. Again, this all is about analysis. It's not how you're supposed to make your algorithm. So if you make all the unions without path compression, you will have some tree in the end. So in this final tree, without any path compression, you assign these ranks. And now we look what will go on in this not compressed tree after we apply path compressions. So when we call find operations from here, we follow this path and then apply path compression. And now we'll look what's going on when we apply path compression. Yeah, sounds like that. Okay, hope it's more clear. So let's go back. Again, we call find operation from this x. We follow this path and then apply path compression. So to calculate the time complexity, we need to calculate the length of this path, yeah, and to calculate sum of all these lengths. So first, let's calculate the sum of all final edges from each class. So for each class, we take the last edge from this class. Like we have, this is the only edge from x1. For class 2, we have this and this. So this is the final. For class 3, we have this, this, and this. So this is the last edge from this class. So we take only the last edge from this class. Now let's calculate the sum only for these edges. So how many edges in this path are the last edge from the corresponding class? No, it's easy to see that we have z plus 1 classes. Yeah. So we have at most z plus 1 final edges. Yeah. So we have at most z plus 1 final edges. No, final, last, this last here. And yes, like this. Right? So let's add all these all these last edges to the final time complexity. So we have m find operations. For each operation, we have z final edges, last edges. So we have in total we have let's say t1 equal to m multiplied by z plus 1. So this is the first thing we will add to the total time complexity. So for the total time complexity, first we will calculate all these last edges from the classes. This number. Cool. Now let's calculate not the last edge. So let's take some edge from not the last class. So let's have some edge. So we have some edge from class J. And it is not the last edge from this class. So at some point we have another edge from class J. And here we have vertex X. Here we have vertex Y. So this edge from X to Y belongs to class J. And this is not the last edge from this class. So we have this edge from class J and here another edge from class J. Now, what happens when we apply path compression? We will link this X to some vertex here, which is above this vertex here. Let's call them somewhere. So let's call this vertex, let's say U, this V, and this will be, let's say, Y prime. So X was connected to vertex Y, and this edge was in class J. and this was not the last edge from this class. So here we have another edge from the same class. So after we apply path compression, this x will be linked directly to this vertex y prime, right? Cool. So now let's look what happens with the class of this edge. By the way, let's stop here. Let's think. What happens to the classes of the edges? Yeah. If you have this vertex x, it was connected to vertex y, and after path compression, it is connected to some vertex y prime. Wow, your Russian is much better. Each week your Russian is better and better. Okay. So if we have this edge and after path compression we have this edge, what happens to the class of this edge? Let's compare the class of this edge and class of this edge. Will the class be increased, decreased, or stay the same? What do you think? Basically, how will the classes change in the time? So the answer, it may increase or it may stay the same, but it will never decrease. Yeah? Because here, no, it may never decrease, because the rank of y prime, here, the rank of y prime is always greater than the rank of y. So first you have segment like this, and now you have segment like this. Yeah. So the segment becomes longer and longer. Yeah. So if the left border is the same and right border is to the right, then the class will be only increasing. But it may stay the same. Yeah. You may have something like this. You have rank of y here and rank of y prime here. So first you have this segment and now you have this segment. So it belongs to the same class. It's also possible. So when you make this path compression, this rank, this class may be increased or may stay the same. Okay. Now, let's see what happens when it stays the same. So we have some rank j, and here we have this segment. Call it shorter. So this is x, this is y. This is rank of x, this is rank of y. Yeah, just for simplicity, I will avoid this r. Right? Okay. This is rank of x, this is rank of y, and this segment belongs to this layer. So I have something here, something here. So here. No, these are two consecutive numbers in this sequence. Good. I'll just simplify this picture as much as possible. Hello. Okay. That's very strange timing to raid me, but okay. Okay. It's not very beginning for the lecture, sorry. And it is the middle of the lecture, so. So, now what's going on? We have this edge from x to y. Yeah? This edge belongs to class J. it means that in the sequence J, these x and y are between two consecutive values. So we have this sequence J, and we have two consecutive values here, and this x and y are between these two consecutive values. Now, if it is not the last edge from the same class, then we have another edge from the same class. Yeah, this edge UV. So we have another edge UV here. And then above this vertex V, we have this new vertex Y prime. So after we make this path compression, we connect this X directly to this Y prime. So we have some. Again, this is what happened when you make a path compression. We never change the ranks. Ranks are always fixed. No. Ranks are always the same. We change the classes. The class will change. When we go from here to here, the class will be increased. Ranks are always the same. Now, let's see. So the rank or the class of this edge may stay the same. So if we have this edge and this edge, then we have this edge. So the class of this edge is the same. But it may not happen a very long time, because let's see. If this edge belongs to class J, it means it does not belong to class J minus 1, obviously. Let's look on J minus 1. So we assign class J to this edge xy. It means we cannot put them between two consecutive values in J minus 1 sequence. It means that in sequence J minus 1, these two ranks belong to different segments, right? So we have some partition here. So we have the same partition here, we have the same partition, but we also have some. So sum of elements of sequence J minus 1 is between x and y. So it's somewhere here. And the same for this edge UV. It also belongs to class J. It means that we cannot put it in class J minus 1. It means that in class J minus 1, there is some partition between U and V. So in the previous sequence, these two ranks are not in one segment, and these two vertices are not in one segment. So there is some element of the previous sequence between x and y, and there is some element between y and v, well, u and v. So there is some element here and some element here. So after we make this path compression, we connect this x directly to this y prime. So now we have at least two elements in the previous sequence. So now we have two elements of sequence J minus 1 between x and y. So after we make path compression, the number of elements of previous sequence between x and y is increased. Let's write this here. So when we go from here to here, number of elements of sequence J minus 1 between x and y is increasing. Okay, that's the most complicated part. Again, what happens? We have this edge, we have this edge, and we connect this directly to this. Both these edges belong to class J. If they belong to class J, J is the minimal sequence we can put between two consecutive values. Yeah? So we cannot put this x and y between two values on the previous sequence. So in the previous sequence, if you look on x and y, they will be divided by some element of sequence J minus 1. And the same for these two vertices. for these two vertices in sequence j-1, there is some element which divides them. So after we make this path compression, we connect this x to this y prime, and now there are two elements of the previous sequence between x and y, and so on. After each time we go through this edge and apply the path compression, the number of these elements of the previous sequence will be increased between x and y. Yeah? So we have x, we have y, here we have one element, here we have two elements, and so on. Each time we apply the path compression, the number of elements will be increased. And the number of elements here is b minus 1. And because for each next sequence, we have the previous sequence with step equal to b. So we here we have the same elements as here, but with step equal to b. So we take first element, then we have b element, and so on. Well, again, here the element k multiplied by b power j. This is k plus 1 b power j. And so this element is kb b power j minus 1. And this is k plus 1 b multiplied by b in power j minus 1. Yeah? Are you alive? That stuff is a little bit complicated. So again, let's look on this in the sequence J. These two elements are between k multiplied by b power j and k plus 1 by b power j, just by definition. Yeah? So if you look on the previous sequence, you have the same values here because this is divisible by b in power j minus 1, and this is divisible by b in power j minus 1. So you also have these two elements. Each new sequence is subsequence of previous sequence, right? Okay. I just give you some time to get what's going on. So you have the same elements. You take some elements from previous sequence and get only them. So in the previous sequence, between these two elements, there were another b minus 1 elements. Because you take each element with step to b. You take this element and this element, but you didn't take these elements. So here you have some another b minus 1 elements between these two elements. That's basically all. So here, each time you increase the number of elements between x and y, and there may be at most b minus 1 elements between x and y. So if you each time you increase this number, you may do it at most b time, right? Yeah, this is subsequence of this. Again. What is wrong? What's wrong? Yes, each sequence is subsequence of previous sequence. Here I take all the numbers divisible by b in power 2. Next will be all numbers divisible by b in power 3. What? You have some strange sequences. Again, well, let's move here. So if b equal to 2, so 0 subsequence will be 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. 1 will be 1, 2, 4, 4, 6, 8, 10, 12, and so on. Now it will be 4, 8, 12, 16, 20, 24, and so on. Each next sequence is a subsequence of previous. So here you take these elements. Here you take only these elements. And so on. So each time you pick every second element from the previous sequence and get the new sequence. Okay? So if you look on two consecutive elements of some sequence and find them in the previous sequence, there will be another b-1 elements between them. Like here. If you take two elements like 4 and 8 here, if you take these two consecutive elements and find them in the previous sequence, there will be one element between them. You have some strange sequence. There is no powers of 2. How did you get this? Now, each sequence is a simple arithmetical progression. But the step of progression equals to b in power j. Okay. Yeah, here is it. Okay. So, again, if you take two consecutive values and find them in the previous sequence, there will be b-1 values between them. And every time you apply the path compression, the number of elements is increasing. So you may apply path compression for this edge at most b times. After you apply it b times, the edge from x will be moved to the next class. So if you have this edge in class J and you apply path compression to this edge at least b times, then the number of these values between x and y will be more than b. It means that you cannot fit this edge in between these two values. So the class of this edge will be increased. So, so let's calculate the total time we do all this. T2. So we have n vertices. For each vertex, we make b path compressions, and then this edge is moved to the next class. We can move the edge to the next class at most z times. So we need nb and then multiply by z. Nice. So again, we have n vertices. For each vertex, we have this edge. We apply b times apply path compression, and then the class of this edge is increased. There are at most z classes, so we can increase class at most z times. So we apply path compression b times, move to the next class. Apply path compression b times, move to the next class. total number of operations will be n multiplied by b multiplied by z. True? Okay, this is a complicated lecture. It's okay if you don't understand some details. The goal is to make just some impression of the proof. You can rewatch the lectures later. Oh, finally, good question. Good. The only problem is this all is true when we have not the final class. We have the fixed number of classes. We have these normal classes, and then the class z plus 1, which is kind of different. Yeah. So we have these z classes. So this is true for all classes. So these are last edges. These are non-last from classes at most j. And now we need to calculate the non-last edges for class z plus 1. Yeah. Let's calculate. So if we have vertex on class z plus 1, and it is not the last edge on this class. So we have edge on class z plus 1 and another edge on class z plus 1. What happens to this class? Exactly the same thing. For this edge, when we apply path compression, the number of elements in sequence z will be increased. So if it has class z plus 1, we have the same. So they are in class z plus 1, this class z. So if this edge xy is in class z plus 1, it means we cannot fit it in class z. So in class z, there is some value between x and y, and also between u and v. So after we apply path compression, there will be two values in sequence z between x and y. Let's try to calculate the total number of elements in sequence z. So let's look on sequence z. We have these values. These values are different ranks, right? So we need only values which may be ranks of some vertex. So we need only values at most n. Yeah. So let's look on this final sequence and let's find all the values which are at most n. Because rank is at most z, at most n. Yeah. Yeah. So we need to fit some of these values between rank of x and rank of y. Rank of y is at most n. So let's find the number of elements in the last sequence which are no more than n. No, it's easy. It's n divided by 2, right? Right? When we apply path compression b times, what happens to the actual tree? In a single application path compression, what we reach at the root directly. We may reach the root directly, why not? So yeah. We walk not to the real root of the tree, but to the current root. So we walk until we reach some dash edge here. So here you have some future edge. Yeah. So we walk to here and then apply path compression. Yeah. That's okay. That's really complicated stuff. That's why it's not in the main course. Okay. Now, let's calculate the total number of non-final edges from class z plus 1. For class z plus 1, each time, if it is not final edge, we apply path compression. The number of elements from sequence z is increasing. Total number of elements in sequence z is at most this. So, have T3 for each vertex. When it is in class z plus 1, we can make at most this many, right? Let me see. No, looks fine. Yeah, at most this many operations. Right? That should be right. Yeah? Okay. So these are non-last. Whew. That's all. So the total time complexity will be combined of 3 parts. First part, the last edges from each class. We have that many edges. Then we have non-last edges from all classes except the final class. We have this number of edges. And this is the number of last edges from class z plus 1. Now we just take sum of all these values and get the final complexity. Well, let's go. So the final time complexity will be T1 plus T2 plus T3. Well, let's see. So it is mz plus m plus n multiplied by b. B equals to this. And z equals to this. And plus this the n. Is it? Looks fine. Okay. So it is n squared divided by m over n power log n over m. Looks kind of not right. Is it fine? Well, let's check. Okay, let's do it. Oh, this is also z. This is should be. So we can change this. Yeah, so we have mz plus mz. So this is mz plus m. Well, I can skip this m because I need only asymptotics, right? So this is mz, this is mz. So this is mz plus this. What happens to this? Okay, so this is mz, this is m, this is mz. Right? So I'll just skip all this. Now to here. What happens to here? So I need to m divided by m in power. So what it will be? I am not good in mathematics. Okay. Let's see. I have m over n power this. Or 1 over would be 2. Yeah, right. So here, if you take m over n power 1 over log m over n, you will have 2, right? So you take m over n and take it into the power 1 divided by log m over n. So this part is actually 2. And now you have 2 in the power log of n squared over m. So you have 2 in the power log square of m. You have n squared over m. So this all is n squared over m, right? Right. And now you divide n squared by this and you have m. Yeah, fine. Whew. So again, this is big O of m multiplied by z. Again, this is the final time complexity is this. That's all. This is the final time complexity of the path compression without rank heuristics. So if you just apply path compression without rank heuristics, you will have this time complexity. Whew. Are you alive? Okay, let's look at this just a little. So what does it mean? It means again it's a function of n and m. Let's have some corner cases. So what happens if the next part will be much easier. We'll do the same but with Ackermann function. The idea of the next half will be the same. We'll just do everything the same but with Ackermann function. It's not the middle of the lecture. It's more like three-fourths of the lecture. That's good enough. Yeah, good enough. So let's move here. Let's go here. So if you don't apply rank heuristics, you just make unions in any way, and you make only path compression. This will be a total time complexity. Let's see. For example, what happens if, let's say, if m is about equal to n? So what will happen? Here you have some constant, and here you have log n. Yeah. So if m is about n, then the time complexity is log n. Right. If m is about n squared, then what will happen? Here we have some constant, here we have some constant. So time complexity will be constant. What does it mean? It means if you have a lot of queries, of find queries to your union find data structure, even if you don't make any heuristics, you make only path compression, then if the number of your find operations is at least n squared, then time complexity of each find operation will be constant. That's what I was talking before. Like if you make many operations with the data structure, it became faster and faster. So if you make small number of operations, time complexity will be log n. If you make many operations, time complexity will be constant. If you make something in between, no, time complexity will be something in between. Okay, you ready for Ackermann? Whew. Okay, let's take the final step. Now we'll do everything the same. We'll do everything the same. But for the balance tree, if we apply rank heuristics and path compression, I need to erase everything, because if you have any questions, ask them now. Okay, let's go. So, that's why we have something like this. So you don't want this denominator to be equal to 0, yeah, right? So if m equal to n, then here you have log of 1, you have 0. It's kind of strange, yeah. So you need to have something like that, yes. So you need these constants to avoid the situations. Whew, let's go. Whew. Yes, if m is about n square, you also have some zeros. Yeah, so you need to adjust some constants to avoid this all these corner cases. Yeah. Okay. Now we will do all the same things, but with rank heuristics. So when you apply rank heuristics, you have some balanced tree, and the only property we need about balanced tree is the following. Let's look on the balanced tree. Let's look on the ranks. Okay. If we look on vertex, if the rank of x equal to k, then the number of vertices here is at least 2 in power of k. And it means that in the tree there are no more than n over 2 in power of k vertices of rank k. That's the only property we need from the balancedness tree. So if you apply rank heuristics, yeah, the tree will be balanced. And if it will be balanced, you will have this property. It's quite obvious. I think we discussed this when we talked about okay, so that's the only thing we need about rank heuristics. Now let's go. We will do all the same tricks, but we will use different sequences. So in previous proof, we use only simple sequences. So each sequence was some arithmetic progression. Here we'll use some more complicated sequences. Let's see. So there are different ways to introduce Ackermann function. I will use the same way as in the paper I suggest you to read. So let's introduce them like this. Let's have sequence 0. Sequence 0 will be like this. You have integers 0, 2, 4, 6, 8, and 12. That's all. Very simple sequence. Now, Now, every next sequence will start with 0 and 2. So here I have 0, 2, 0, 2, 0, 2, 0 and 2. And now, strange thing, now to fill all this part, we will use the following recurrent formula. J will be equal to A, I minus 1, A, I, J minus 1. Now we will use this formula to fill all the values in these sequences. So, for example, in this sequence, what value should we put here? We take, again, this is the value to the left. So we take this value and go to the previous sequence and find the element with this index. So we go to this value, use it as an index, and find the element of this index in the previous sequence. Well, let's see. These are indices. Very simple formula. So we take this number, find in the previous sequence the element of this index, so it will be index 2, so it's 4, and put this 4 here. Here we take 4, find in this sequence element of index 4, and put this here. Now again, we take this 8, find the element of index 8, it will be 16, and 8. This comes from, that's the standard definition of Ackermann function, basically. That's how the Ackermann functions valid. There are little bit variants, but basically this is how the Ackermann function works. Ackermann function is, I'm not sure where it was introduced first. It has some fundamental properties. So it is some kind of fundamental function in mathematics. So I'm not sure where exactly it was introduced first, but that's an Ackermann function. Yeah, that's exactly like dynamic programming. Yeah. But we don't need to calculate these values. We just need to write them for this analysis. So the first sequence is just arithmetic progression. The second sequence is powers of 2. So we have powers of 2, we have 16, here we have 32, here we have 64, and so on. What happened to the next sequence? Here we take this number 2, go in the previous sequence, take element of index 2, it will be 4. Actually, all elements here will be 4. Now here we take number 4, take the fourth element in the sequence, it will be 16. Now we need to take 16th number in this sequence. So 16th number, so this sequence contains powers of 2, so this will be 2 in power 16. And here we need to take in this sequence the element of index equal to 2 in power 16. So this element will be 2 in the power of 2 in the power 16, like this. And so on. So here will be 2 in power of 2 in power of 2 in power 16. And so on. So again, this sequence grows very slowly. This sequence grows exponentially, and this sequence grows very fast. What happens in the next sequence? Oh, it grows very fast. Now here, for this value, you need to take fourth value from here, so it will be 2 in the power 16. And here you need to take value from here with index 2 in the power 16. So you need to take like the tower of these powers of length equal to 2 in the power 16. So it is very big. And in the next sequence, even this number is very big. So you need to take fourth number from this sequence, or like this number. It is already very big, so you will never use this number. So each next sequence grows much faster than the previous sequence. Oh, Ackermann published in 1928. Okay. Okay. Good to know. Cool. That's all. Now again, each next sequence is subsequence of the previous sequence, obviously, right? Yeah. So each next element is some sequence of sequence I-1. So you take each time you take some elements from the previous sequence. Now we will apply all the same technique. We will say again. First we have this sequence 0, 2, 4. Let's put them closer. We have the 0, 2, 4, 6, 10, 12, 14, 16, and so on. Here we have 0, 2, 4, 8, 16, and so on. Here we have So again, this is sequence 0, this is sequence 1, sequence 2, sequence 3, and so on. And we will write Z such sequences. We will pick some number Z, and we will write Z such sequences. And Z will be equal to inverse Ackermann function of Ackermann. So that will be the final time complexity. Spoilers. Again, let's pick first Z sequences from this table. And then we do exactly the same as the previous proof. We take some edge and assign a class. So we assign class K. So if we can put, this is X, this is Y. If we can put X and Y between two consecutive values of some sequence, of sequence K, then we say that this edge have class K. Exactly the same definition as before. That's all. That's all. Now let's calculate everything. So how to calculate total time complexity? Again, we have, let's look some path. Yeah? We have some path from X. On this path, we have some classes. For each class, we have some last edge from this class and not last edge. So let's calculate them all. So let's get T1. Let's calculate the last edges from each class. We have Z classes. So we have Z final edges. So will be, for each query, we have at most Z final edges. Yeah, this is last edge from each class. From each class, we take only the last edge. Now, let's calculate not last edges. What happens when you calculate not last edge? Now again, you have some let's call class. You have some edge on class J. Yeah? What happens when it's not last class? You apply path compression. Then you have another edge, UV, and this Y prime. So you apply U2 here. Yeah, let's just write it here. Write it here. So in sequence J, you have this X and Y between these two values. So this value is a let's make it I. So if class equal to I, so this is ij, and this is a ij plus 1. So if the class of this edge equals to I, it means that these two ranks are between these two values. Yes, if we use rank heuristics, the rank will be at most log n. That's true. This will reduce, but not significantly. Yes, we will adjust this alpha to. Okay, well, let's adjust this alpha first. This alpha will be the minimal I such that I m over n is at least log n. Like this. So he will use the. I think it's not important, but. Yeah, good enough. Good enough. Let's go back. That's not very important. This is interesting. So let's go back. So if we have this edge on class I, yeah, it means that both these ranks are between these two values. And it is not in class I minus 1. It means that in class I minus 1, there is some value between x and y. So when this edge is not the last edge from this class, it means there is another edge from the same class, and this is y prime. So after path compression, we will have this, and we will have another value here. Again, like before, if we have two edges from the same class, after we apply path compression, we link this x to this y prime, so the number of these values from the previous sequence is increased. Right? So what is the number of elements here? Let's calculate the total number of elements in sequence I minus 1 between Aij and Aij plus 1. No, it's quite easy. If you look on this sequence of this element, so this element is actually I minus 1 Aij. So if you look on this element, its index in the previous sequence, is Aij. Let's meditate a little bit. So, okay, what I want to do, I want to apply all the same technique as in previous proof, but for different sequences. Yeah. How did we make it last time? We calculated, we have three parts of our time complexity. Last edges, not last edges from all class except z plus 1, and we have class z plus 1, of course. In class z plus 1, there are all edges which doesn't fit in this class. Okay. And we have non-last edges from classes up to z, and we have non-last edges from class z plus 1. Exactly like before. How we calculate time complexity? We look when we see this edge is not the last edge from the same class, from class I, then there is another edge from the same class, then there is some element here, so the number of elements between x and y is increased. So to calculate total time complexity, we need to calculate the total number of elements between this. We have partition here, we have partition here. We need to have number of all partitions in the previous layer. What is this number? This number, I claim this number, is at most Aij. Is it clear? Is it clear? No, because of this. Because this is how this is exactly how I define this number. This number equals to this. So it is element of the previous sequence with this index. So again, this Aij is the index of this element in the previous sequence. So actually, no, Aij is the number of all elements before this. Actually, it is no, number of in this segment is no more than this. Okay, I give you some time. You don't need more strict upper bound. Yeah, that will be enough. Yeah, you may have difference between this and this, but this will be enough. I claim that's good enough upper bound. Yeah, it looks like it's not strict enough, but it actually is good enough. Now let's go. Let's calculate. So let's take all nodes in this range. So let's take all nodes with ranks between this and this. What is the total number of nodes between this and this? So we have rank x be at least Aij and less than Aij plus 1. What will be the total number of nodes in this segment? No, it will be sum for k from Aij to Aij plus 1. For each rank, let's calculate the maximal possible number of nodes on this rank. It will be up to this. So it will be no more than this multiplied by n to n power. And that's no more than 2n power. Right? So I have this geometrical progression. I just change it to infinite progression. Yeah. And then convert this infinite progression to 2n. So it will be 2n and just have this. Yeah. Looks fine. Are you still here? What is this r in the exponent? This k. Okay, k. So I try to find the total number of nodes between these two values, with ranks between these two values. So I iterate over all possible ranks in this segment. And for each rank, calculate the maximal possible number of nodes of this rank. So it's then I make the upper bound. I change this with plus infinity, have this series, convert the series to the 2n, and have 2n divided by this. Looks fine, right? This is the maximal possible total number of nodes in this segment. Now, for each node in this segment, we may need to make this number of path compressions. So we take all these nodes and apply this number of path compressions to these nodes. So the total number of this is T2. So we do the following. We make sum for all I from 0 to z. So we iterate for all layers. For each layer, for each class, we take all elements in this segment and apply this number of iterations. So we take this sum for j from 0 to, I don't know, something not important. And for here we iterate for all classes, iterate for all segments. For each segment, we take all nodes in this segment. It will be 2n over 2 in power aij. This many nodes, and for each node, we need to make this number of operations. Whew. That's all. Now again, this sum is just some series. You can this is some constant. So again, this is no more than sum 2n multiplied by sum x divided by 2 in power of x. Okay. Yeah. This sum is sum of something divided by 2 in the power of something. So I will change this sum with this series, and the sum of this series will be big O of n. I'm not sure about constant. Some constant doesn't matter. So each sum like this is actually linear. So t time will be big O of Zn. Okay, this may look like some magic. Okay, it's actually pretty easy. Well, if you think about it, it's all happens because of this. Because the number of nodes of class k is at most n over 2 in power k. So if you look on number of nodes in some range of ranks, if you take some range of ranks and take the sum of all nodes in this range, you will have some sum of geometrical progression, so it will be still constant. That's all the trick. So because of this, we have this sum of geometrical progression, so we have linear something linear here, and then we take this, put it here, and again we have some sum of progression, so we get something linear here. So in the end, here we have something linear, here we have something linear. So for each layer we have some linear sum. So total number of non-final steps in each class will be linear. Here's the fact that the sum of expression over those I and j would intersect us is lesser than the sum of expression. Yeah. So here I have the sum for some values for here, and here I just add all other values x and take sum of all possible x's. So this sum is less than this sum. Yeah. Whew. That's all. That's almost all. Ух ты. It's more than 2 hours. Good. Okay, final step. Again, we have this T1, we have this T2, and we need to have T3. It will be non-last edges on the class Z+1. So this class Z+1 is again is a little bit different. I will prove only the yes. In this lecture, I prove only the upper bound. Yes, you can prove the lower bound as well. Again, I highly suggest you to read the paper. Let's go back. So we have this T1, it's the last edges, and here we have non-last edges of rank not last from class up to Z. And now we need to calculate the number of edges on class Z+1. This class Z+1 is special. In class Z+1 we have edges which don't fit in these classes. Again, this will be simple. For each edge in class Z+1, each time we make the path compression, the number of values from sequence Z will be increased. So we need to calculate the total number of elements in sequence Z. And the total number of sequence Z, like here, will be at most m over n. So in sequence Z, we need only elements which are no more than log n. Yeah, because here. And we especially pick the Z in such a way that in sequence Z we will be no more than m over n elements, no more than log n. All the ranks, again, all the ranks are less than log n. In the last sequence, we only need elements up to log n, and we have no more than m over n elements in the last sequence. So in the last sequence, yeah. So for each node, if it is not the last node in the sequence, so we will have up to m over n. Yeah, right. So these are not last nodes in class Z+1. Again, this is because of this. We especially pick the number of layers in such a way that in the layer Z, there will be no more than m over n values, no more than log n. Whew. That's all. Here we have mz, here we have nz, here we have n. So we have this plus this plus this, and it will be so total time complexity will be m alpha n. That's all. Isn't it great? Okay, if you miss some details, you may rewatch the lecture later. That's not some topic which you may understand from the first try, but I highly recommend you to read the paper and rewatch the lectures if you miss some details. Okay, thank you. It was a cool bonus lecture. So I hope to see you again.